So when we graph it, we get -10, and we plot a little bit above it. 0, 1. Wait a second. No, I'm not plotting it. That's the bad thing. This is the cutoff equation. I have to talk about translations now. We've got to talk about these translations and what happens. So now that I look at the translations, I'm going to move all of these points left 0.4 and then down 2. So let's see. The old point was -10 and then a little bit above. Now I'm going to move half a little over, but then down 2. So it's a little off. We're looking outside here. We're off the grid. But then 0, 1. So 0, 1 used to be here, but now I'm going to move half a spot over and then down 2. So it's about -0.4, -1. 1, and then this is approximately 1.5. So if I go over 1, up 1.5, I'm moving over a half and then down 2. I'm like in the middle of this box. I'm going to connect the points using the growth shape. Notice the growth shape. Growth shape should always take on this asymptote first approximation and then getting bigger. So the growth shape should look like this, unless it was a negative leading coefficient. Then it would be a flipped. Let's talk about domain, range, and asymptote. So if we have some type of shift outside of the function moving up or down, that's also going to adjust this number. And the asymptote looks pretty similar to it also. So just want to recap. The first thing we had to do was distribute this 0.4 to clean it up so I could make my cut. I determine if it's growth or decay so I can get my shape and so I can determine what numbers am I supposed to plug in. After you plug in these numbers, you're using the translations. These are old points and then you move them accordingly so you don't have to constantly plug in so much into your calculator. Okay, so let's get down a new formula for real-life problems. This is for continuously compounded interest. Those are key words. Continuously compounded interest. It's got to happen continuously. If it was compounded quarterly, we use a different equation. If it was compounded monthly, it's a different equation. But if it's compounded continuously, that's when we're using this Purdy formula. I call it Purdy because P-E to the R-T, per T. It's a per T formula. Thanks for the chuckle. Appreciate it. All right. Let's label these. A is the accumulated amount. The R. If you get a problem and it says, hey, in 6 months' time, how much am I going to have? I have to realize, wait a second. What needs to go up here is it should be in years. So 6 months would be written as 0.5 up here. So just want to stress that. All right. So now as we read this example 8, you deposit $1,500 in an account that pays 7.5% annual interest compounded continuously. What is the balance after 1 year? So because of this, I choose this formula. So 1,500 is the principal, 0.075 is the rate, times 1 is the time. I'm ready to calculate all this. We talked about how sometimes it's easier if we clean up this exponent first and then put it in our calculator. So we're going to round this to 2 decimal places because what's the balance after a year? We're dealing with money here. Since we're dealing with money, I want to end it to the nearest cent, just because that, in this context, makes the most sense.